In this chapter, we study the classic vehicle routing problem. The goal is to design routes for a fleet of vehicles so that all customers are served while total travel cost is as small as possible. You can think of this as the operational question every delivery company faces each morning. Which truck should serve which customers and in what sequence, so the day finishes on time and at a reasonable cost? The scenario is citywide delivery operations. Global Logistics Inc. starts from a central distribution center and must reach customers spread across many neighborhoods. The operations manager must balance practical realities such as vehicle capacity, driver working hours, fuel consumption, and traffic patterns. Even small improvements in routing can translate into meaningful savings and better service quality. Vehicle routing becomes intractable very quickly because the number of possible visit sequences grows explosively as the number of customers increases. For example, a 10-location problem already implies 362,880 possible routes. At 20 locations, the count is over 2.4 quintillion, which makes exhaustive search unrealistic for everyday operations. This slide summarizes the key complexity takeaways. Vehicle routing is a generalization of the traveling salesman problem, so it inherits the same hard, combinatorial growth. The practical implication is that you usually need a spectrum of methods, from exact formulations for small cases to heuristics, learning-based systems, and advanced optimization for large, changing environments. This chapter is organized as a tiered toolkit. Tier 1 provides a rigorous mathematical baseline. Tier 2 introduces a classic heuristic that decomposes the problem. Tier 3 uses a population-based meta-heuristic to explore solutions. Tier 4 adds continual learning for dynamic settings. Tier 5 expands into a digital twin view of the whole system. Tier 6 treats vehicles as autonomous agents. Tier 7 builds a human and artificial intelligence partnership. Tier 8 adds ethical constraints. Tier 9 introduces quantum-inspired optimization via the quantum approximate optimization algorithm. Tier 1 starts with the mathematical formulation. We represent the depot and all customers as vertices in a directed graph, and we allow travel between any two distinct vertices. Binary routing decisions indicate whether a particular vehicle travels from one vertex to the next. The objective is to minimize total travel cost across vehicles, and the constraints enforce that each customer is visited exactly once and that routes are operationally feasible. This slide defines the sets and parameters. The vertex set includes the depot, labeled as 0, and all customers, labeled from 1 through n. We also define the directed edge set, the vehicle set, the travel cost between vertices, the demand for each customer, and the capacity of each vehicle. These are the building blocks used by the objective and the constraints. The core decision variable is a binary indicator that equals 1 when a vehicle travels from one vertex to another. We also use a load variable that tracks how much demand the vehicle is carrying after leaving a vertex. Operationally, that load tracking is what prevents infeasible routes. It forces the route to respect vehicle capacity and helps eliminate disconnected subtours that do not return to the depot. The objective is straightforward: minimize the sum of travel costs over all vehicle moves that are actually used. This captures the key economic driver of routing. Lower total distance and better sequencing reduce fuel and labor costs, and they also tend to improve service reliability by avoiding unnecessary detours. These constraints ensure each customer is visited exactly once across the entire fleet. They also ensure that each vehicle leaves the depot at most once. Together, they prevent duplicated service and prevent a single vehicle from being assigned multiple disconnected trips. This is fundamental for making the solution interpretable as real daily routes. Flow conservation constraints ensure continuity. If a vehicle enters a vertex, it must also leave that vertex, which is what turns individual edges into a connected tour. The degree constraint limits how many outgoing arcs a vehicle can take from any vertex. Combined, these constraints produce clean route structures rather than scattered edge selections. Capacity feasibility is enforced by propagating load along the route. The load after leaving a node must be consistent with the load before it, adjusted for the demand served. Load bounds also ensure that the carried load never exceeds the vehicle capacity and never drops below the demand served at the current customer. This prevents solutions that look cheap on paper but cannot be executed by a real vehicle. This slide states the domain of the routing variables. Each edge decision is binary. It seems simple, but it matters because it makes the problem combinatorial. The combination of binary decisions and constraints is what leads to the explosive growth in the number of possible solutions. The figure visualizes the network flow representation of the vehicle routing problem for a small instance with 2 vehicles. It helps you see how the depot connects to customers and how each vehicle selects a sequence of arcs that forms a route. This kind of visualization is useful when debugging formulations and validating whether constraints are doing what you intended. In the concrete example, a depot serves 6 customers with 2 vehicles, each with capacity 15 units. Demands are 3, 4, 2, 5, 3, and 4 units. Vehicle 1 serves customers 1, 2, and 3 with total demand 9 and cost 42. Vehicle 2 serves customers 6, 5, and 4 with total demand 12 and cost 38. The total cost is 80 and both routes respect capacity. Tier 2 uses the cluster first, route second idea. Instead of solving the whole routing problem at once, you first partition customers into capacity feasible clusters. Then you solve a traveling salesman-style routing problem inside each cluster. This decomposition reduces complexity and is often good enough for medium-scale daily planning. This figure shows the decomposition strategy, the clustering step groups nearby customers while respecting capacity, and the routing step sequences, visits inside each cluster. The intuition is that geography drives travel cost, so building clusters based on spatial proximity and demand often produces sensible routes quickly. In this part, you can see the implementation details in action. Key functions in this chunk include cluster, first route second. You will notice logic related to demand, route. As you read it, focus on the sequence of steps and which variables are carried forward because that is where most implementation bugs hide. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. In this part, you can see the implementation details in action. Key functions in this chunk include nearest neighbor TSP. You will notice logic related to route. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also, check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. In the Tier 2 example, a 12-customer problem is solved with 3 vehicles of capacity 20 each. The clustering phase creates 3 geographical clusters with loads 18, 19, and 16. Within each cluster, a nearest neighbor route is built. Producing costs 67, 73, and 58 for a total cost of 198. The key lesson is that this is achieved in 0.03 seconds, while exact methods can take many minutes or longer. Tier 3 introduces the multiverse optimizer. You maintain a population of candidate solutions, each treated as a universe. High-quality universes influence others through exploration mechanisms, poor universes are discarded, and wormholes trigger local improvements. The practical goal is to escape local optima and find better route sets than simple heuristics can provide. This figure illustrates the 3 core mechanisms used by the multiverse optimizer: exploration, exploitation, and local refinement. The idea is to combine broad search with targeted improvement, so the population steadily evolves toward lower routing costs while still maintaining diversity. In this part, we move from the idea to the mechanics of the implementation. Key functions in this chunk include Multiverse Optimizer VRP. You will notice logic related to fitness, population, iteration. As you read it, focus on the sequence of steps and which variables are carried forward because that is where most implementation bugs hide. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. If arrays or tables are involved, double-check indexing and alignment, because off by 1 mistakes are common in time and sequence code. A practical check is to print or log a few intermediate quantities, so you can verify that the update logic behaves as expected. In this part, the code makes the slide method executable. Key functions in this chunk include white-hole rate and wormhole local search. You will notice logic related to route, fitness, iteration. As you read it, focus on the sequence of steps in which variables are carried forward because that is where most implementation bugs hide. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. In this part, the code makes the slide method executable. You will notice logic related to route, fitness. As you read it, focus on the sequence of steps in which variables are carried forward because that is where most implementation bugs hide. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. In the Tier 3 example, a 25 customer instance with 4 vehicles is optimized using a population of 50 universes over 1,000 iterations. The best solution improves from cost 456 to 312, which is a 31.6% improvement. Wormhole local search contributes about 8% improvement when it occurs, and the algorithm reduces wormhole probability in later stages to emphasize stability. Tier 4 addresses dynamic routing where conditions change. The idea is to learn routing strategies over time while avoiding catastrophic forgetting. Elastic weight consolidation preserves important parameters from earlier scenarios, and replay memory stores representative past decisions. This lets the system adapt to new traffic patterns and customer distributions without losing what worked before. The figure shows the continual learning framework. It highlights how new data is incorporated, while an importance-aware mechanism protects critical learned knowledge. This is valuable in logistics because routing conditions change continuously, yet the system must remain reliable day after day. In this part, we move from the idea to the mechanics of the implementation. The key class visible here is the Continual VRP learner class. Key functions in this chunk include initializer, forward, and compute Fisher information. This part is especially about loss computation and experience replay. As you read it, focus on the sequence of steps in which variables are carried forward, because that is where most implementation bugs hide. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. In this part, we move from the idea to the mechanics of the implementation. Key functions in this chunk include consolidate knowledge, EWC loss, and train continual. This part is especially about loss computation, gradient updates, and experience replay. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. In this part, we move from the idea to the mechanics of the implementation. Key functions in this chunk include solve dynamic VRP. This part is especially about step-by-step simulation, loss computation, and experience replay. As you read it, follow the data flow from inputs to outputs, and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. If feasibility is enforced with penalties or repair steps, confirm the penalty scale is large enough to prevent invalid outputs from looking attractive. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. In this part, we move from the idea to the mechanics of the implementation. You will notice logic related to route. As you read it, focus on the sequence of steps and which variables are carried forward, because that is where most implementation bugs hide. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. In the example, the company operates in 3 districts with different traffic patterns. Training begins on morning rush hour in District A with cost $245. When adapting to District B, the approach achieves cost $289 compared to $312 for retraining. Replay memory stores 2,500 historical route decisions, enabling faster convergence in the third scenario and delivering 15 to 20% better performance than static methods. Tier 5 reframes. Vehicle routing as part of a larger system. A digital twin builds a virtual replica of vehicles, warehouses, traffic networks, and customer behavior. Because the digital twin syncs with real-time data, it enables what-if testing and predictive planning. The point is to optimize not just routes, but the entire operational ecosystem. This figure shows the system of systems view. Telematics, warehouse systems, traffic data, and customer interfaces all feed into a unified simulation and decision layer. A well-designed digital twin helps managers evaluate changes safely, such as fleet expansion, new service areas, or seasonal demand shocks. In the concrete example, the digital twin covers 150 vehicles and more than 500 customers across 3 metro areas. GPS updates arrive every 30 seconds. What-if analysis shows that adding 5 electric vehicles cuts fuel costs by $2,400 per month, while adding $800 of charging cost. Rush hour rerouting reduces average delivery time from 45 to 32 minutes. And on-time delivery improves from 87% to 94%. Tier 6 shifts from centralized planning to distributed autonomous decision-making. Each vehicle becomes an agent capable of bidding for tasks based on position, capacity, and cost. Auctions and negotiation protocols allow rapid reallocation when conditions change. Coalition formation allows agents to coordinate multi-stop routes that reduce joint cost and improve utilization. This figure visualizes a multi-agent ecosystem, where vehicles coordinate through communication and market-based mechanisms. The key takeaway is that local interactions can create emergent global efficiency, and the system can self-heal when disruptions occur. In this example, 75 vehicles serve more than 400 customers daily, and auctions allocate hundreds of tasks per hour. A task receives multiple bids, such as 11.70 and 10.20. The winning vehicle then forms a coalition with another vehicle to reduce cost by 22%. System metrics show a 15% reduction in average delivery cost and fast reassignment, around 3.5 minutes after a vehicle breakdown. Tier 7 emphasizes that routing is not only computation. Human dispatchers bring context, customer relationships, local constraints, and on-the-ground realities. The Centaur model combines AI recommendations with explainable reasoning and human overrides. Over time, the system learns from overrides and reduces the need for manual correction, while keeping humans in control for exceptional cases. This figure shows the collaboration loop between human operators and the AI system. The AI proposes routes with confidence and rationale, the human reviews and adjusts, and the system records the justification to improve future predictions and planning. In the example, the AI system plans 45 deliveries for 8 vehicles with estimated cost $1,240 and completion time 6.8 hours. Dispatcher Sarah overrides a recommendation based on a real operational detail, a slow loading dock. After she records the justification, the system updates service time estimates and recomputes routes, improving on-time performance to 94% and reducing costs by 11%. Tier 8 embeds ethical principles into routing decisions as explicit constraints. The point is to avoid trading fairness, environmental stewardship, labor safety, or community impact for small cost savings. By making ethical metrics measurable and enforceable, the routing system can remain aligned with stakeholder values and regulatory expectations. This figure presents a constitutional framework that constrains routing decisions. It emphasizes that ethical guidelines are not afterthoughts. They are encoded into the optimization process so that the system only proposes routes that meet the agreed principles. In the example, fairness requires that no zip code has average delivery time more than 1.5 times the system average. Emissions are capped at 2,500 kilograms carbon dioxide equivalent per day, and labor rules limit work hours and require breaks. Community impact constraints restrict heavy vehicles during school hours. Costs rise about 8%, but retention improves 15% and volume increases over time. Tier 9 introduces the quantum approximate optimization algorithm. The problem is converted into a quadratic binary form that quantum hardware can evaluate using hybrid optimization. The method alternates between cost-focused and mixing operations, and a classical loop tunes parameters. The promise is faster discovery of high-quality solutions for very large instances where classical methods struggle. This figure shows the circuit architecture used to implement QAOA for routing decisions. The important concept is that quantum superposition and structured interference help explore many configurations, and the hybrid loop pushes probability mass toward better solutions. In the example, 25 vehicles serve 100 customers. The hybrid setup uses a 64-qubit processor with 8 circuit layers and 200 parameter iterations. After 4.2 hours, it finds a cost of $3,247 compared to $3,685 for the best classical meta-heuristic after 48 hours, which is about 12% better in the reported case. These practice questions help you translate the concepts into implementation. They range from writing a complete formulation, to coding the heuristic, to designing learning-based and multi-agent approaches. Use them to test whether you can go from the problem description to a working solution method, and to understand the trade-offs between solution quality, computation time, and operational realism. The vehicle routing problem is foundational in logistics because it captures the daily challenge of serving many customers with limited vehicles. A complete toolkit ranges from mathematical baselines to practical heuristics, learning systems, digital twins, autonomous coordination, ethical constraints, and even quantum-inspired methods. The key is choosing the right level of sophistication for the scale and volatility of the operation.